It's time to extend our toy models to handle more complex tasks. First, we will introduce nonlinearity to our neural models. Instead of the linear model we have been using, we will now incorporate nonlinearity by passing the weighted sum through a nonlinear function. Different conventions exist for the subscripts of weight parameters, but in modern computer languages, subscripts typically start from 0. Two common nonlinear functions are the softmax and ReLU functions. The softmax function is used to normalize a vector into a probability distribution. Mathematically, the softmax function is defined as follows. ReLU is a simple and popular nonlinear function used in neural networks. It outputs the input value if it is positive, and 0 otherwise. Our task is to train a neural network to recognize handwritten digits using the MNIST dataset. Here are 9 samples from the MNIST dataset, each consisting of a 28 by 28 pixel image and a corresponding label representing a digit from 0 to 9. The architecture of the neural network we will use is fully connected. Before we can start coding, we need to address some issues. Firstly, how do we input an image into the neural network? For example, if we have a 4 by 4 pixel image, one approach is to flatten the image pixels to create one-dimensional data. This means the input layer will have 16 neurons, or units. In the case of the MNIST dataset, the input layer will have 784 units. The next question is how we encode the outputs, specifically how the 10 categories for digits 0 to 9 are represented. Handwritten digit prediction is a multi-class classification task where samples are categorized into specific classes without overlap. Each sample is assigned a single label from 0 to 9. Various encoding methods can be used for these categories. Decimal encoding requires 1 unit to output numbers 0 to 9 for the labels. Binary encoding necessitates 4 units, unary encoding requires 9 units, and one-hot encoding needs 10 units. One-hot encoding is typically preferred for single-label multi-class classification tasks. So we choose 10 units for our model. We also choose 128 units for the hidden layer. For comparison purposes, I will code using both PyTorch and TensorFlow. Let's start with the PyTorch code. First, we need to import the datasets and transforms libraries from Torch Vision. If they are not available, you may need to install Torch Vision as it is not pre-installed in Colab. Compose combines a list of transforms into a single object that is applied to the input data. In our case, we have 2 transforms in our list. The first one converts the pixel data into tensors, which we have already done in our linear regression example. The second transform maps the pixel values to a smaller range, which we will discuss later. I typically store datasets in my Google Drive. To access my Google Drive content, expand the side panel by clicking the folder icon. Then click on the Google Drive icon. Navigate to the Drive directory, then to My Drive, where you will find the Dataset folder. Right-click on it. Select Copy Path, and you're all set. Torch Vision provides a variety of built-in datasets in the Torch Vision.Datasets module, along with utility classes for creating custom datasets. When the download parameter is set to true, the dataset is fetched from the internet and saved in the specified directory. If the dataset is already downloaded, it will not be downloaded again. I will explain the terms training, testing, and validation later. Please note that datasets.MNIST does not return a conventional list that you can iterate over. You need to utilize a data loader to access the individual data points. The MNIST dataset contains 70,000 grayscale images of handwritten digits from 0 to 9, split into 60,000 training images and 10,000 test images. This division allows for effective training and evaluation of machine learning algorithms. Let's analyze the class net. The flatten function is responsible for converting 2D images into 1D data. The first linear layer has 128 units, receiving 784 input values from the previous layer. The second linear layer contains 10 units, receiving 128 values from the previous linear layer. The forward method provides nonlinear activations. In our model, we use the rectified linear activation function for the hidden layer and the log softmax for the output layer. Log softmax applies a softmax followed by a logarithm. I will talk about the dimension parameter later. We use cross-entropy loss for training. Later, I will demonstrate an issue when combining log softmax and cross-entropy loss. The training process is standard, followed by plotting the loss as a function of epoch. Next, we will restart the session to address the issue of combining log softmax and cross-entropy loss. This time, we will remove the log softmax activation and rerun the code to achieve similar results. Before conducting further investigation, I would like to try Colab's AI coding assistant. I want to extract some examples from the MNIST dataset before defining our neural network. To do this, we insert a cell and click Generate to instruct the Colab system on our requirements, which will generate the code accordingly. There are 4 options available. Running option 1 provides the desired output, while options 2, 3, and 4 result in the same error. The pixel values are scaled to range from 0 to 1. Our PyTorch code also scales the images. I will address the technical problem later. Initially, I mistakenly defined this model. Here is the correct model I intend to build. In TensorFlow, the model infers the input to a layer from the previous layer. The PyTorch equivalent is shown here. The model is compiled in TensorFlow, but PyTorch does not require a compilation step. When we provide the parameter metrics with a list of metrics, the training process will record these metrics. We are now prepared to train our model. Surprisingly, I accidentally ran the code with the wrong model, and it still worked. I am unsure why. Next, we will evaluate how well the model performs on unseen data. The results are promising. The loss value is expected to be higher than the final training loss, and the accuracy lower than the final training accuracy. This indicates that the model generalizes well. What have we learned? Regardless of the machine learning libraries we utilize, the models we have employed are essentially mathematical functions. In the context of linear regression, a linear function was utilized. For handwritten digit recognition, a complex function comprising two types of nonlinear functions arranged in layers was employed. The training process involves minimizing a loss function by adjusting parameters to align the outputs with the expected values, known as labels or targets. This form of learning is known as supervised learning. We will delve further into the fundamental principles of machine learning and address technical challenges in upcoming videos. Thank you for watching.